Hello everybody, welcome to the second part of this presentation on the energy functional of Hitchin representations. This will be a continuation of the first part, so in particular I will be using the notation that was introduced in the first talk. So if you have not seen this talk before, I recommend you watch it first. Let's begin with an overview. In the first part we introduced the energy functional and discussed why it is a quantity that's interesting to study. And now in this second part, I will discuss two results regarding the energy functional, and these are section 3 on the strict plurisubharmonicity of the energy functional and section 4 on the energy functional rigidity. Let's begin with the strict plurisubharmonicity of the energy functional. And in order to discuss the results, let's first define what plurisubharmonicity exactly is. So we consider a function on a complex manifold called Y with values in the real numbers. Then this function is called plurisubharmonic if it is subharmonic on every holomorphically embedded disk. To be more precise, we consider any embedding of the unit disk in the complex plane into our complex manifold, and we're looking at a holomorphic embedding. We compose this embedding with our function and ask for this composition of functions to be subharmonic on the unit disk. And if this condition holds for all these holomorphic embeddings, we call F plurisubharmonic. And then we call F strictly plurisubharmonic if the composition is actually strictly subharmonic on each holomorphic embedding. And with this definition out of the way, the first result that I want to discuss can be easily stated. We consider a Hitchin representation into one of the following groups: PSL-NR, PSP-2N, PSO-N+1, or the exceptional group G2. Then we consider the energy functional as I introduced it in the first part of this talk. And the result states that this energy functional on Teichmüller space is a strictly plurisubharmonic function. And let me mention that this result extends previous results of Tromba. He considered a slightly different situation, namely he considered the energy functional of harmonic maps between hyperbolic surfaces. But if you translate what he did into our notation, then he proved that the energy functional is strictly plurisubharmonic in the case of Fuchsian representations, i.e. Hitchin representations into PSL and R. So if we consider Tromba's result as a statement on these Fuchsian representations, then we see that the above result does generalize this directly because Hitchin representations generalize Fuchsian representations. As I mentioned in the first part, the energy functional is interesting mainly because of its role in the study of the Hitchin components, and the major theme in the study is whether the Laborie conjecture holds. And with an eye on this conjecture, let's mention the following corollary, which states that from the strict plurisubharmonicity of the energy functional, we get a very weak convexity result of the function. And it's really quite a weak convexity result, but nonetheless it's there. First, we need to know that the condition that the energy functional is strictly plurisubharmonic is equivalent to the following condition here, meaning that the complex Hessian of the energy functional is a positive definite bilinear form. So we choose coordinates of Teichmüller space, and if you remember, Teichmüller space has real dimension 6g minus 6, so it has complex dimension 3g minus 3, and we denote these coordinates by z, and then the Hessian can be written like this, and we ask for this to be a positive definite sesquilinear form. And the corollary of our previous theorem can be given as follows. It follows that the Hessian, and I'm talking here about the real Hessian of the energy functional, is actually positive definite on a subspace of real dimension 3g minus 3. And this holds at any point in Teichmüller space. The reason for this is that the real Hessian of a function composes into 4 blocks. Well, let me say that again. The real Hessian of a function on a complex manifold composes into 4 blocks. One of these blocks corresponds to the complex Hessian we've written over here. And saying that the complex Hessian is a positive definite bilinear form means that one of the blocks of the real Hessian is also positive definite, from which follows that there's a subspace of real dimension 3g minus 3 on which the real Hessian is positive definite. So we get from our strict plurisubharmonicity result that the Hessian has some positivity in it. Because I want to discuss 2 results in this talk, I will not go into too much detail on the proof of the result of the strict plurisubharmonicity. Rather, I will give an overview of the tools that are used. Mainly, we build on the previous work of Toledo. He considered a more general situation, namely the energy functional for harmonic maps into general Riemannian manifolds. However, we can apply his results to our situation, and his results imply immediately that the energy functional is plurisubharmonic. That means that for our proof, really what we're interested in is putting this strictly plurisubharmonic. In order to do that, we need the following fact from Toledo's paper. What he does is he considers a holomorphic embedding of the unit disk into Teichmüller space, and he derives a formula for the Laplacian of the composition of these 2 functions, and this formula is entirely in terms of the derivative of the associated harmonic maps. And this is a very important point for our proof. So Toledo proves the plurisubharmonicity of the energy functional by deriving a formula for this composition, the Laplacian of the composition, and he shows that it's non-negative. However, in order to conclude that it's strictly positive, we do not have enough information when you just stare at this formula. We need to know a little bit more in order to push this further. And for this we use that the representations we look at are Hitchin representations. That means that the harmonic maps that appear in the formula for the Laplacian of the composition are these equivariant harmonic maps for Hitchin representations. And for such equivariant harmonic maps, we have a little bit more information than we would otherwise have. Namely, it's a fact that Hitchin representations can be related via the non-abelian Hodge correspondence to Higgs bundles on the surface. And this is this Hitchin parameterization that we also mentioned in the previous talk. And this relation between the representation and a Higgs bundle on S gives us a lot more information about the derivative of the harmonic map we're looking at. Namely, a Higgs bundle consists of a complex vector bundle and a Higgs field. And it turns out that the Higgs field entirely determines the derivative of the harmonic map. These can be related to each other. And this is the extra information that we use. We know rather explicitly what the Higgs field looks like, and we plug this information into the formula that is derived by Toledo. And this information is enough to conclude the strict positivity of this term here. And that's the, well, the admittedly rather broad overview of the proof of this theorem. And with that, let's move on to the second part of this talk. In this part, we take a rather different approach to the energy functional. We consider things from a slightly different angle, because the energy functional plays such an important role in the study of Hitchin components and Hitchin representations. I would like to ask the question more generally: how much information about a representation, in particular a Hitchin representation, is actually encoded in its energy functional? And to make this question more precise for this presentation, I asked the more specific question: is a representation determined by its energy functional? And this you must always ask, is it determined up to conjugation? Because conjugating a representation does not change its energy functional. And it's this question that I'm going to discuss in the rest of this talk. In particular, what I am aiming towards is the positive statement that a Hitchin representation is uniquely determined by its energy functional. And what I'm going to discuss is a road towards proving this. However, it's still a work in progress, so I will end the talk with a discussion on which parts are still missing in the proof. But in the road towards proving this, we see some interesting sub-results. We consider a simpler setting. We rather than considering a representation, we consider simply a non-positively curved metric on a surface S. Then we have the following fact, which is kind of an analog of the result of Corlett that we saw in the first talk. Namely, for every complex structure on S, there exists a unique and energy-minimizing harmonic map that's homotopic to the identity, and it maps from S equipped with a complex structure into S equipped with the non-positively curved metric. And armed with this fact, we can define an energy functional in precisely the same way that we did in the first part of this talk. So we consider again the energy functional of this non-positively curved metric, which is a functional Teichmüller space, which assigns to each equivalence class of complex structures simply the energy of the corresponding harmonic map. Our first result relates the energy spectrum to the simple length spectrum of H. So let's first introduce what the simple length spectrum is. If gamma is some free homotopy class of closed curves on S, then we consider the length of this homotopy class to be the shortest length of a loop in the homotopy class. And this is measured with respect to the metric H. So LH of gamma really is the length of the shortest geodesic loop that lies in the free homotopy class. And now the simple length spectrum of a metric is simply the vector that records all the lengths of the simple closed curves in the surface. So we let script S be the set of all homotopy classes of simple closed curves in S, and the simple length spectrum is simply the length of all these homotopy classes. And now the main result of this section is as follows: that the energy functional of the metric H determines its simple length spectrum. A little bit more precisely, suppose you have two metrics H and H prime. Suppose that their energy functionals coincide. Well, then their simple length spectrums must also coincide. And this has the following corollary. We can get some rigidity results for metrics using the energy functional. Namely, there are several classes of metrics on the surface which are known to satisfy simple length spectrum rigidity, meaning that a metric in such a class is determined uniquely up to isotopy by its simple length spectrum. Two rather elementary examples perhaps of this are the following. It's known for hyperbolic metrics on a surface that such a metric is uniquely determined up to isotopy by its simple length spectrum, and it's also known for this a particular class of singular flat metrics that are induced by quadratic differentials, and this was proven by Duchesne, Leniger, and Ravi. And if we combine this fact with our theorem of the previous slide, we immediately obtain the following corollary, that a metric in the set of hyperbolic metrics or the set of singular flat metrics induced by quadratic differentials, such a metric is determined up to isotopy by its energy functional. And this is kind of a program that we would also like to run for representations. Know that the energy functional of a representation induces its simple length spectrum, and then hope that there exists a suitable rigidity theorem to say that such a representation is then uniquely determined by its simple length spectrum. This is something we're going to see in the next couple of slides. But before we do this, let's first look at the proof of the theorem that the energy spectrum determines the simple length spectrum in the case of surfaces where things are easier. A main ingredient in the proof are Dehn twists, so let's first introduce what those are. We let gamma be some simple closed curve, and then a Dehn twist around gamma is a homeomorphism of the surface that twists the surface once around gamma. To be more precise, we take a color neighborhood of gamma, which we identify with a cylinder, and on this cylinder we let the Dehn twist be the map that's given by this formula. And then outside of the cylinder, the Dehn twist is simply the identity map. And it means that if you have, for example, a curve that runs straight through this cylinder, its image under the Dehn twist is this curve which wraps around it once. If you have a Dehn twist, it induces a natural map on Teichmüller space. And if we consider Teichmüller space as I've introduced it in the first part of this talk, namely as a set of complex structures on S up to isotopy, then this natural map can be given by the following formula over here. And what you should think of here is really that we change the marking of a point in Teichmüller space simply by composing with the Dehn twist. Well, with the Dehn twist defined, we can now give a few words on how the proof works. We pick first some point in Teichmüller space and hit it with a increasing number of Dehn twists. So we pick a point and Dehn twist it more and more, and we consider how the energy functional changes when we do this. It's known that the energy functional is proper, so it will increase. And the main idea of our proof is that the asymptotic rate of increase does encode the length of the curve we're Dehn twisting around in the target manifold. More precisely, it turns out that there exist constants C1 and C2, depending on the curve around which we Dehn twist and the point x we chose in Teichmüller space, such that the following asymptotic inequalities hold. We consider our point X and Dane twist it n times around gamma. And then the energy of this resulting point can be estimated as follows. Its asymptotic growth rate is as n squared, and in the factor in front of n squared, the length of the curve gamma is encoded. The reason for this is as follows. When you start Dane twisting often around gamma, we obtain a very big mismatch between the structures of our domain and our target. In particular, around gamma, the domain and target look very different. This means that any harmonic map will have to have a very high energy, which harmonic maps do not quite like because they are energy minimizing maps. And in order to minimize the energy as best as they can, what they do is they try to map as big a part of the domain surface into the color neighborhood around the simple closed curve gamma. In this way, they can minimize the stretching by kind of spreading it over as much of the domain surface as possible. And by letting n go to infinity, it turns out that the harmonic maps approximate the map that just collapses the entire surface into gamma and rotates n times around it. And what you see here in the formula over here is that the energy of the harmonic maps approximates the energy of this collapsed map. This collapsing map has precisely the energy has precisely the same asymptotic energy as you see here. And now to finish the proof, what we do is we find a sequence of points in Teichmüller space such that these constants C1 and C2 converge to a common value. What you can then do is divide these inequalities by n squared, let n go to infinity, and what you see then is that you have in the middle a value that's entirely determined by the energy spectrum of our function. And on the right or left hand side, you see that we can read off the length of our curve gamma in the target manifold. And this is possible because C1 and C2 converge to the same common value. And in this way, we can extract the value of this quantity over here simply from the energy spectrum. That's kind of a overview of how the proof works. And let's now look at how we can go further. Namely, many of these techniques can also be applied to Kleinian surface groups. So a Kleinian surface group is a representation of the fundamental group of our surface into PSL2C. And this representation needs to be discrete and faithful. We note that PSL2C acts by isometries on the hyperbolic free space. So we can take again a quotient of the hyperbolic free space by the image of our Kleinian surface group to obtain some hyperbolic free manifold. And for this hyperbolic free manifold, we can define a simple length spectrum as we did before for surfaces. And we call this simple length spectrum also the simple length spectrum of the Kleinian surface group. And now many of the arguments that I outlined in the previous slides also work in this case, and we obtain the following theorem, that the energy functional of a Kleinian surface group determines its simple length spectrum. We combine this with a result of Bridgman and Canary, who proved that the simple length spectrum of a Kleinian surface group determines the Kleinian surface group up to conjugation. Simply combining these two statements gives us the following corollary. If you have two Kleinian surface groups, rho and rho prime, then if they have the same energy functional, then they are either a conjugate or one is conjugate to the complex conjugation of the other. And in this way we see that it is true that at least for Kleinian surface groups, the energy spectrum does encode a lot of information about the representation, in fact enough to identify it almost uniquely. I would like to run a very similar argument for Hitchin representations. However, it's not yet complete. Let me discuss what difficulties you encounter when you try to run pretty much the same argument. I believe that the Dane twisting argument also works for Hitchin representations, meaning that you get a statement similar to the ones we saw before, that the energy spectrum of a Hitchin representation does determine the simple length spectrum of a Hitchin representation. What you then are looking for is some similar statement that the simple length spectrum of a Hitchin representation determines the representation uniquely. And there is some work in this direction by Bridgman, Canary, and Laborie. However, they consider a different type of simple length spectrum. Let me briefly say what the difference is. If you look at a simple closed curve in the fundamental group, what they consider is the spectral length of the image of this element of the fundamental group. And this is defined as follows. Rho of gamma is a matrix, say in PSL and R. It has a number of eigenvalues, and then the spectral length is the largest eigenvalue of this element. However, using our method, we do not obtain the spectral length of an element here. What we obtain is the translation length of the element, which is the shortest distance that this element translates when it acts on a symmetric space. So in order to close the circle of ideas that I discussed here, what we need to know is whether a Hitchin representation is determined by its simple translation length spectrum. And this is different from what is proven before, where it's proven that a Hitchin representation is determined by its simple spectral length spectrum. So this is something to consider in the future. And with that, I come to the end of my presentation. I thank you all for your attention.